Hi, in this video I'm going to start section 4.3 from the book, which is second order linear homogeneous equation with constant coefficient. So if the coefficients are constant like a number, then we call that is a second order linear homogeneous equation with constant coefficients. Okay, now so how does the equation look like? This is a y double prime plus by prime plus cy equals to 0. Okay, so the prime stands for the derivative. A, B, and C are constant. So if you want to write this in the standard that form that we saw in chapter 3, then you can divide both all the terms by A, then you get y double prime plus b over a y prime plus c over a y equals to 0. Okay, so do you remember how did we change this into the system of first order linear differential equation? How did we do? We assume that x1 equals to y and x2 equals to y prime, right? And then we get x1 prime equals to x2, right? Because if you find the derivative of this, you will get x1 prime equals to y prime, but y prime is actually x2. So x1 prime is x2 and x2 prime is y double prime. If you solve that, you get negative c over a x1 minus b over a x2, because x1 is y and then x2 is y prime. Okay, so now if you write this in the matrix form, then you can write x1 prime x2 prime matrix equals to, which we denote by vector x prime, which is equals to, since this can be written as 0 times x1, okay, plus x2 1 times x2, so you can write 0 1 and then here negative c over a negative b over a and x1 x2. So this is written in the form of x vector x is equals to a matrix A times x, right? So how did we do after that in chapter 3 is we find the eigenvalues, right? To find out the eigenvalue, you first need the characteristic equation. You know how do I find the characteristic equation? Is lambda squared minus sum of the diagonal elements, sum of these two elements, right? And then plus the determinant of this matrix A. Okay, so what is the determinant of this matrix A? Determinant is this times this minus this times that. Okay, so this times this minus this times that, it will give you 0 and then minus negative c over a, so that will be positive c over a, because minus negative c over a, that is the reason. Okay, so lambda squared minus negative b over a is the sum of that, right? And then times lambda plus the determinant is c over a equals 0. So if you factor out a 1 over a, then what do you get? You get a lambda squared plus b lambda plus c equals to 0, right? So what are the eigenvalues? Eigenvalues are the solution of the characteristic equation, right? So the eigenvalues are the solution of this equation. For eigenvector, what we do after we find out the eigenvalue, to find out the eigenvector, we assume that let vector v is an eigenvector. Then the definition is a v equals to lambda v, where a is this matrix, right? And the v, let us assume that v is v1 v2. Let us say that v is equals to v1 v2, and then a times v equals to lambda times v, right? Now you solve it. So on the left side there is a product of the two matrices, so 0 times v1 is 0 plus 1 times v2, that is v2 equals to lambda v1. Similarly, negative c over a v1 minus b over a v2 equals to lambda v2. If you take the first equation, what do you get? You get v2 equals to lambda v1. If you take v1 equals to 1, what do you get? v2 equals to lambda. Hence the vector v, the eigenvector v, is 1 comma 1 and then lambda. Okay, that is the vector. Okay, thus for lambda the solution is x equals to e to the lambda t times v. That's how we find out the solution, right? So it is e to the, if lambda is the eigenvalue, then e to the lambda t times v, where v is the eigenvector corresponding to that eigenvalue lambda. So if you write the value of v, then 1 lambda e to the lambda t 1 lambda, that is a vector x. But vector x is basically x1 x2, right? Because we wrote that vector x prime is x1 prime x2 prime, so vector x is x1 x2, right? This is what we use. So x1 x2 equals to e to the lambda t, and then lambda times, you just distribute this to this and distribute this to that, lambda times e to the lambda t, right? Which is equals to, what is the value of x1? x1 is y and then x2 is y prime. So you can write this as equals to y prime, because the top one is x1, the bottom one is x2, so y and y prime, right? Now since the given equation is in this form that has just y, so y is the solution of this equation, right? Y double prime y, so just the y is the variable here, so y is the solution here. So you see that y equals to what? X1, right? X1 is e to the lambda t is a solution of this star. So the solution of, if you have the eigenvector lambda of this second order linear homogeneous equation with constant coefficient, then its solution is y equals to e to the lambda, that eigenvalue, times t will be the solution. Okay, let us summarize what we just did here as a theorem. So let lambda be the root of a lambda square plus b lambda plus c equals to 0. Then y equals to e to the lambda t is the solution of this star. So one of the solution is y equals to e to the lambda t. And lambda is an eigenvalue of the matrix A. So to find out the eigenvalue, you don't have to change into the pair of two equations, two linear ODEs. Okay, you don't have to do now. What you can do is you can just replace A times y double prime will be lambda square plus b y prime means lambda plus c. Okay, equals to 0. That's what you do. And then solve that equation and you will get the eigenvalue. Okay, lambda is an eigenvalue of the matrix A, that matrix A. And the vector x equals to e to the lambda t, lambda e to the lambda t is the solution of the system. X equals to x prime equals to ax. Okay, so this is what we saw it here. Okay, now so we see that lambda is the root of this equation, right? So that lambda can, so there may be more than one lambda, okay, or repeated lambda. So what are the possibilities of lambda? The root of this equation, a lambda square plus b lambda plus c equals to 0, can be either real or distinct. It is a quadratic equation in lambda, right? So real or distinct. When do you get real or distinct? If b square minus 4ac is greater than 0, we call discriminant, right? So if the discriminant is positive, then you will get two real and distinct unequal values of lambda. If b square minus 4ac is 0, then you get real and equal. And if b square minus 4ac is less than 0, we get complex conjugate. So you will get two complex eigenvalues. Okay, guys. So what I'm going to do next is I'm going to mention this thing on the theorem. Okay, guys. Let us do that. Alright, the theorem here is let lambda 1 and lambda 2 be the solution, because this is a quadratic in lambda, right? So it will have two solutions, lambda 1 and lambda 2. Then the general solution of this equation ay double prime plus by prime plus, which is a second order linear homogeneous equation with constant coefficients, a, b, c and are constant, right? Then the general solution of this will be y equals to c1 e to the lambda 1 t plus c2 e to the lambda 2 t if lambda 1 and lambda 2 are not equal. So whenever you solve this equation, okay, and then if you get the two lambda values are different, equal and real and different, then this will be the final solution. Okay, that will be the final solution, general solution, I would say. This will be the general solution of this equation. Okay, if lambda 1 and lambda 2 are equal to each other, the solution of these two, if you get the repeated roots or if you get the two equal roots, at that time they are similar. Only the difference is there is one extra t, right? And then there is lambda 1 and there is lambda 1. So both of them will have, because if they are equal, lambda 1 and lambda 2 are equal to each other, right? So the solution, general solution at the time is y equals to c1 e to the lambda 1 t plus c2 times t and then e to the lambda 1 t again. When is that? If lambda 1 and lambda 2 are equal to each other. But if the lambda 1 and lambda 2 are the complex and unequal, because whenever you get a complex root, so you will get a complex conjugate, right? In that case, this is the solution of this equation. C1 e to the mu t. Mu is basically the real part of the eigenvalue, right? And then cosine nu t and mu cosine nu t minus nu sine nu t plus C2 e to the mu t sine nu t mu sine nu t plus nu cosine nu t. Okay, so this is the general solution in that case. If the roots of these equations are complex, then that will be the solution of this equation. Okay, guys. All right. Similarly, if you write this into the form of the pair of first order linear equation, then in that case, the general solution of x prime equals to a times x. A is 0, 1, negative c over a, negative b over a times x, is vector x equals to x1, x2, which is equals to y and then y prime, where vector x equals to it's the same thing, right? We do c1 e to the lambda 1 t v plus c2 e to the lambda 2 t v, right? So the v is 1 lambda 1 1 lambda 2 if lambda 1 and lambda 2 are not equal. If they are equal, then you will see that t times there, okay? So c1 e to the lambda t lambda 1 t 1 lambda 1 plus c2 e to the lambda 1 t t 1 plus lambda 1 t. So we have done this in chapter 3, similar thing, okay? And then if they have the complex root, conjugate complex root, then you will get c1 e to the lambda t, sorry, mu t and cosine nu t. So you got exactly the same thing there, all right? So this is what is the general solution for the second order linear homogeneous equation with the constant coefficient, which is this equation, okay? Now what are the equilibrium points? If c is not equals to 0, if this c is not equals to 0, or in that case if this c is not equals to 0 in the pair case, then you will get 0 0 is the only critical points, okay? That's what you will get. So 0 0 will be the only critical point in the system of system of first order linear equation, okay? So to find out the stability of 0 0, whether it is stable or unstable, you look at the sign of the eigenvalues, okay? So the eigenvalue you get from here, you will check the sign. If lambda 1 and lambda 2 is less than 0, then 0 0 is asymptotically stable, meaning that when t tends to infinity, when you increase the value of t, then you should be able to get 0 0 stable, meaning all the solution approach to 0, the origin, okay? When the real lambda values are negative. If the real lambda values are positive, then 0 0 is unstable. If lambda 1 lambda 2 have the opposite sign, one is positive, other is negative, then we call 0 0 is unstable saddle, okay? It is called a saddle point, and saddle point is considered unstable there. And number 3 is if lambda 1 and lambda 2 are complex, then 0 0 is stable, spiraling. If the real part, that is mu is, it's exact same concept. If mu is negative, then 0 0 is spiral in. All the solution will go to 0 0. And if that is positive, if mu is positive, real part of lambda I means both of the lambda 1 and lambda 2 have mu on the real part. If they are positive, then it will be unstable, right? And also if the real part is 0 0, in that case lambda 1 and then 2 will be just I times nu, right? Plus minus I times nu. In that case you will get purely imaginary eigenvalues. In that case we get 0 0 as center. You know what that means from chapter 3, okay? That is called center, and then center is considered as stable, okay? So the next we want to do some examples. So let us see the first example. The first example is solve y double prime plus 3y prime plus 2y equals to 0. So as we did in chapter 3, I don't want to change this into the pair of two first order linear equation. What I want to do is I want to use the concept we just discussed. That is, first of all, I want to find out the eigenvalue. How do I find the eigenvalue? I write the characteristic equation. How the characteristic equation look like? It will be lambda square plus 3 lambda plus 2 equals to 0. So for the double prime, you write lambda square. For this term, you write 3 lambda, and then for the last term, you write without that y. This is the characteristic equation, okay? Let us find out the solution of this. What do you get? Lambda plus 2 and then lambda plus 1 equals to 0, right? You got that. If you multiply, you get 2. If you add, you get 3 lambda. So basically you got lambda equals to -1 and -2, right? That's what you get. These are the eigenvalues. So how would the general solution look like? General solution is, because the formula says that y equals to c1 e to the lambda 1 t negative t, right? And then plus c2 e to the negative twice t. That is basically the solution, okay? That is the general solution of general solution of the given equation, okay? Now, but the question is asking, so this is a question number 2 from your book, okay? So the question is also asking write the solution in the form of like system of linear ODEs. You know what? Whenever you solve the system of linear ODEs, how would you solve at that time? You were writing x1, x2 formula, right? So this is basically the solution for x1, right? Because y is x1. So what what is the x2? X2 will be, because do you remember that how did we solve that? So what we did there is, in this case, for the given equation, you were writing x1 equals to y, and then x2 equals to y prime, and then solution will be x1 x2 format, right? Now, so we have x1, we have the values for x1, but what is the value for x2? X2 is y prime. So what is y prime? Let's find out y prime from here. So y prime is equals to the derivative of that, negative c1 e to the negative t, and minus 2c2 e to the negative twice t. I'm just finding the derivative of y with respect to t, right? So what do you get then? Therefore x1 x2, which is same as y and then y prime, you write, just combine these two, okay? So that will look like c1, so it will look like c1 e to the negative t, and then minus c1 e to the negative t, right? And then plus, I can write c2 e to the negative twice t, that is the component of y, and then this one is negative 2c2 e to the negative twice t. Now what I want to do here is I want to take out the common thing. So here what is common? c1 e to the negative t is common, right? So c1 e to the negative t is common. You can write 1 negative 1, right? And then plus c2 e to the negative twice t is common. So you can write 1 negative 2. So this is the final answer, okay? And also the question is asking how would the so what is the equilibrium point here? Equilibrium point is so since c is not equals to 0, right? You see that this is c, right? This is c is not equals to 0, then 0 0 is the only critical point or equilibrium point, right? Critical point. So how do I know the stability of this? Since the sign of lambda are both negative, it will be asymptotically stable. 0 0 will be asymptotically stable. Asymptotically stable. That's what you get. Now if you want to see how would this look like in the phase portrait, that's what the question is asking. What I need to do is I need to first convert this into the pair of system of linear ODE. What do you get? You take x1 equals to y and x2 equals to y prime, right? And what is x1 prime? X1 prime will be x2, that will be y, and then x2 prime will be, you need to move that to the right side, right? And then you will get negative 1. I'm sorry. So let us look at that. This is what you get, okay? If you write this as a pair of system of linear ODEs, you write x1 prime equals to y and x2 prime equals to negative 2x and minus 3y. So if you enter that, this is what you get. You see that? So it is going from wherever your initial condition is, okay? Wherever you have initial condition, it is always going to the origin. That's what we got, okay, guys? So so origin is basically asymptotically stable. When t tends to infinity, then all the solution goes to 0 0. That's what you get, okay, guys? That was question number 2 from your book, section 4.3. So I want to do one more problem. So it is question number, I want to do question number 31. This is initial value problem, okay? So first of all, we find out the eigenvalues. How do I find the eigenvalue? We use the characteristic equation, okay? So solution. So the characteristic equation is lambda square for this plus 4 lambda for this plus 5 is equals to 0, okay? Now I need to solve for lambda. So can I get the factors? I need two numbers whose sum is 4 and product is 5, positive. So there are no such numbers. So what I want to do is I want to use the quadratic formula, negative 4 plus minus under the root 4 square minus 4ac, right? C is 5 divided by 2 times 1. What do you get? Negative 4 plus minus under the root 16 minus 20, right? Because this is 4 times 5. Negative 4 divided by 2. So what do you get? Negative 4 plus minus 2i divided by 2. If you split, you will get negative 2 plus minus I. So this is what we got. Okay, so we got two complex eigenvalues which are conjugate to each other. Okay, now what I want to do is I want to use the formula that I mentioned earlier. Okay, I want to use the formula that I gave you earlier. If there are if the eigenvalues are complex, what is the formula? Hence, let me write down that formula. Hence, y is equals to c1 e to the mu t, and then cosine nu t, right? And then plus c2 e to the mu t times sine nu t. This is the formula. Okay, now we plug in that. So what do you get? C1, what is mu? So mu plus I nu. So mu is -2, nu is 1, right? So you write e to the negative twice t and cosine t, because nu is t. Nu is 1, that's why. So plus c2 e to the negative twice t and then sine t. This is what you get. Okay, now, so the idea here is we have given the initial condition too, right? So we want to use the initial condition there. Okay, so what is the initial condition? So the initial condition is using y at 0 is 1 and y prime at 0 is equals to 0, right? Oh, we need y prime, so let us write down y prime. So what is y prime? Y prime, oh, you need to use the product rule here, because you see that this is like f times g, right? So what do you get there? So you get c1 times, you get -2 e to the negative twice t times cosine t plus e to the negative twice t times negative sine t, plus c2 times, similarly use the product rule on that, -2 e to the negative twice t times sine t plus e to the negative twice t times cosine of t, because that is the derivative of sine t. Okay, that is the product rule. Now what I want to do is I want to write y at 0 equals to 1. What do you get? If you plug in y at 0, then it looks like this will become 0, this will become 1. So you'll get, so let me use that one first. Let me pull that. So if you use this condition, what do you get? You get 1 equals to, because this is yt, right? So when t equals to 0, that y becomes 1. That's what it is saying. 1 equals to c1, and if you plug in t equals to 0 here, it will be cosine 0 is just 0. So e to the mu times 0 is e to the 0 is 1. So c2 times 0 plus c2 times 0, that is c1 equals to 1. You got c1 equals to 1. Similarly, you want to use this condition. Okay, what do you get? So y prime, this is y prime t, right? Y prime at 0 is equals to 0. So 0 equals to, what I want to do here is I have to plug in t equals to 0. What do you get? You get -2 c1, right, times c1, and this will become 0 because sine 0 is 0. Similarly here, sine 0 is 0, this will become 0 and this will become 1, right? So it will be plus c2. Okay, so what is your c1? c1 is 1. So if you put c1 is 1, then you will get 0 equals -2 plus c2. So you will get c2 equals 2. Right? So what is the final solution? I want to plug in the values of c1 and c2 here at y at t on this equation. Okay, so what do I get? Hence y at t is equals to e to the negative twice t cosine t, right, plus c2 is 2 cosine t, let me, plus 2 e to the negative twice t sine t. This is what you get. Okay guys, this is what you get for the general solution, which is the general solution. Now what do you think? When t tends to infinity, what happens? When t tends to infinity, this will become negative infinity there, right? This will become negative infinity, and this will also become negative infinity. So e to the negative infinity will be 0. So e to the negative infinity here also 0. So basically what you get is cosine is a number between -1 and +1, which is a finite number. Sine is also a finite number for any value of t. Okay, so basically when t tends to infinity, the solution goes to 0. So when t tends to infinity, then y of t goes to 0. So this is how you solve second order linear homogeneous ODE with constant coefficient. Okay, thank you guys.